everyone, my name is Dex Kamitan and today we're going to talk about linear regression. This is a two-part video. For the first part, we will define what it is, talk about its common uses, its assumptions, its hypothesis, and its test statistics. For part 2, we will use SPSS to compute for linear regression. Now, linear regression is the next step after correlation. It is used when we want to predict the value of a variable based on the value of another variable. If you have two or more independent variables rather than just one, you need to use multiple regression and not simple linear regression. For the purpose of this video, we are going to talk about linear regression because multiple regression will be the focus or the topic of our next video. So the overall idea of regression is to examine two things. Does a set of predictor variables or variable do a good job in predicting an outcome or dependent variable, and which variable in particular are significant predictors of the outcome variable, and in what way do they indicated by the magnitude and sign of the beta estimates impact the outcome variable. Now, these regression estimates are used to explain the relationship between one dependent variable and one or more independent variables. But again, for the purpose of this video, we're just going to use one independent variable and one dependent variable. Now, there are many names for regressions dependent variables. It may be called an outcome variable, a criterion variable, an endogenous variable, or regressand. Now, the independent variable or variables can be called exogenous variable, predictor variable, or regressor. So, linear regression is used in three ways. In psychology, regression is commonly used to identify the strength of the effect that the independent variable or variables for multiple regression have on a dependent variable. Typical questions are, what is the strength of relationship between age and short-term memory? Or time spent watching psych nerds video tutorials and exam scores, or even brain size and IQ scores. Second, it can be used to forecast effects or impact of changes. That is, the regression analysis helps you understand how much the dependent variable changes with a change in one or more of the independent variable. A typical question of sort is, how much additional exam point or points do I get for each additional minute of watching psych nerds video lessons? So third, regression analysis predicts trends and future values. The regression analysis can be used to get point estimates. A typical question is, what will my exam scores be in 6 months? However, for the purpose of this video, we are just going to focus on the first and second use of a regression variable or regression analysis. So, linear regression has many types. You have simple regression, which is the focus of this video, where you have one dependent variable, which is in interval or ratio, and one independent variable, which is in interval ratio or dichotomous. The second type is you have multiple linear regression, where you have one dependent variable that is either interval or ratio, and you have two or more independent variables that are in interval or ratio or dichotomous. Then you have logistic regression, where you have one dependent variable that is dichotomous and two independent variables that are interval or ratio or dichotomous in nature. The third type is ordinal, or the fourth type is ordinal regression, where you have one dependent variable that is in ordinal and one or more independent variables that is either nominal or dichotomous. There are other forms of linear regression such as multinomial regression, where you have one dependent variable that is nominal in nature and more than one independent variable or one or more independent variables that is either in interval, ratio, or dichotomous. And then we have discriminant analysis, where you have one dependent variable that is nominal in nature and one or more independent variables that are either interval or ratio. When selecting the model of the analysis, an important consideration is model fitting. Consider that adding independent variables to a linear regression model will always increase the explained variance of the model, typically expressed as R squared or capital R squared. However, overfitting can occur by adding too many variables in the model, which reduces the model generalizability. Occam's razor describes the problem extremely well. A simple model is usually preferable to a more complex model. Statistically, if a model includes a large number of variables, some of the variables will be statistically significant due to chance alone. When you choose to analyze your data using linear regression, part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using linear regression. You need to do this because it is only appropriate to use linear regression if your data passes 6 assumptions that are required for linear regression. For linear regression to give you a valid result. So in practice, checking for these 6 assumptions, just add a little bit more time to your analysis, requiring you to click a few more buttons in SPSS when performing your analysis, as well as think a little bit more about your data, but it's not actually a difficult task. You should not be surprised if when analyzing your own data using SPSS, one or more of these assumptions is violated, that is not met. This is not uncommon when working with real-world data rather than textbook examples, which often only show how to carry out the linear regression when everything goes well. However, don't worry, even when your data fails certain assumptions, there is often a solution for overcoming this. First, let us look at these 6 assumptions. Assumption number 1 is that your 2 variables should be measured at the continuous level. That is, they are either interval or ratio variable. For examples of continuous variables include revision time or review time measured in hours, intelligence measured in IQ score, exam performance measured from 0 to 100, and even weight that is measured in kilograms, and so forth. Now, the second assumption says that there needs to be a linear relationship between the 2 variables. While there are a number of ways to check whether a linear relationship exists between your 2 variables, I suggest creating a scatter plot using SPSS, where you can plot the dependent variable against your independent variable and then visually inspect the scatter plot to check for linearity. Your scatter plot may look something like one of the following. So this is the first 2 examples here show linear relationships. So the third example, which is here, shows that there is no linear relationship between the independent and dependent variable. So if the relationship displayed in your scatter plot is not linear, you will have to either run a nonlinear regression analysis, perform a polynomial regression, or transform your data, which you can all do using SPSS statistics. So assumption number 3 is that there should be no significant outlier. An outlier is an observed data point that has a dependent variable value that is very different to the value predicted by the regression equation. As such, an outlier will be a point on a scatter plot that is vertically far away from the regression line, indicating that it has a large residual, as highlighted in these examples. So, the problem with outliers is that they can have a negative effect on the regression analysis. For example, reduce the fit of the regression equation that is used to predict the value of the dependent or outcome variable based on the independent variable. This will change the output that SPSS produces and reduce the predictability accuracy of your results. Fortunately, when using SPSS statistics to run a linear regression on your data, you can easily include criteria to help you detect possible outliers, and then you can either delete your outlier or do a particular procedure, which I will be discussing later on. So, the fourth assumption is that you should have independence of observation. Which you can easily check using Durbin-Watson statistics, which is a simple test to run in SPSS and is actually integrated in linear regression in SPSS. The fifth assumption is that your data needs to show what is called homoscedasticity, which is where the variances along the line of best fit remain similar as you move along the line. While I will explain more about what this means and how you assess homoscedasticity on your data, you can actually look at this graphs to check or to visualize how homoscedasticity actually look like. So take a look at the three scatter plots here, which provide three simple examples. Two of data that fails the assumption called heteroscedasticity, and one of the data that meets this assumption called homoscedasticity. So the first two here displays heteroscedasticity, and the third here, it should be here, displays homoscedasticity. Now, while these help illustrate the difference in data that meets or violates the assumption of homoscedasticity, real-world data can be a lot more messy and illustrate different patterns of heteroscedasticity. Finally, you need to check the residuals or error of the regression line are approximately normally distributed. Two common methods to check this assumption include using either a histogram with a superimposed normal curve or a normal PP plot, which are both integrated in the linear regression function in SPSS. So you can check assumptions 2, 3, 4, 5, and 6 using SPSS statistics. Assumptions 2 should be checked first before moving on to assumption 3, 4, 5, and 6. I actually suggest that the assumption to check the assumption in this order, because assumptions 3, 4, 5, and 6 require you to run the linear regression procedure in SPSS. So it's easier to deal with this after checking assumption 2. Just remember that if you do not run the statistical test on these assumptions correctly, the result you get when running a linear regression might not actually be valid. So, as I have mentioned earlier, regression can be used for three things: understanding the relationship between predictor and outcome variable, forecasting an effect, and trend forecasting. The hypothesis presented here is only for the first usage, determining the strength of the causal relationship. So the null and alternative hypothesis can be expressed as HO, predictor variable does not significantly predict the outcome variable. And for H1, or your alternative hypothesis, predictor variable significantly predicts the outcome variable. So, lastly, let us look at the linear regression formula. So, a linear regression line has an equation of the form y is equal to alpha or rather A plus B or beta, where X is the explanatory variable and Y is the dependent variable. Now, the slope of the line is B and A is the intercept or the value of Y when X is 0. So to reject the null hypothesis, the p-value should be less than 0.05. So now now that we have discussed the basics of linear regression, let's now head to SPSS to demonstrate how it is computed. So, we will be computing a simple linear regression in SPSS. Let us say you are interested in predicting the online learning self-efficacy of 101 college students from experiencing flow, or a mental state in which a person performing some activity is fully immersed in a feeling of energized focus. So, the predictor or X value is flow. Flow predicts online learning self-efficacy. Theoretically, high levels of flow would predict high levels of self-efficacy too. So let's turn to SPSS. Let's begin with a scatter plot to make sure that we have some semblance of a linear relationship between these two variables. So what you need to do is to go to graphs and then chart builder, and or rather in the gallery. Yes, in the gallery, select scatter plot or scatter dot, then drag simple scatter into the canvas. So in the drop zones for the simple scatter plot, move flow in the x-axis because it is your predictor variable, and then move OLSES or online learning self-efficacy to the y-axis. Now you just have to click on OK. So what you see here in the scatter plot looks like a positive correlation. The dots generally go up, and yep. But let's add the regression line because it's important for looking at linearity. So what you have to do is double click anywhere in the scatter plot, and then uh, in the chart editor, add a regression line by clicking on the icon add fit line at total. So it's this icon. So click, and now you have now you have a regression line. And now you can close the chart editor and your scatter plot is complete. So let's now check some assumptions while we're here. Remember, we talked about these assumptions in detail in the first part of this video. In the scatter plot, the data look linearly related and positive. So as flow goes up, online learning self-efficacy goes up too. Also, the spread of the data are similar, all somewhat similar all along the regression line. They are not cone shaped or curved, so we have established both homoscedasticity and linearity. So we do not need to check for collinearity because there's only one predictor variable here. So collinearity occurs when we have multiple predictors, some of which are correlated amongst themselves. So it's not a problem when we only have one predictor. So now we can conduct the regression analysis. All right, so what you have to do is go to Analyze, click on or hover around Regression, and then click on Linear. So this opens a dialog box for regression. So we are using Flow as predictor of online learning self-efficacy. So put Flow under the independent or independence section, and then move your variable online learning self-efficacy to the dependent variable window. All right. So the method should be left to enter. So what we have to do is go on to click statistics, and then In this box, we have to make sure that we have selected estimate, model fit, descriptives, and Durbin Watson and case-wise diagnosis. So case-wise diagnosis will be used for for understanding outliers. So click continue on your plots, click on your plots and move z predict or z pred to x. This is actually your predictor, and move z resid or residual to y. This is or these are your residual error, and then click on histogram and normal probability plot. All right, so click continue and then click on OK. So, yep. So before we interpret the output, we should check the rest of the assumptions for regression. So as I explained earlier in the video, assumptions for in this assumption section, regression is very sensitive to outlier. So we can check for outliers in the statistics, or rather residual statistics box, and it's here. All right. So we'll look at the standardized residual, which is because they are standardized, can be interpreted like a z-score. So the minimum and maximum values for the standardized residual should not exceed negative 3.29 or positive 3.29 respectively. If they do, you have outliers. If we have outliers, we would stop now with the interpretation, go back to the dataset, examine the scatter plot, and identify the outlier or outliers. So you could then delete the entire case, or you could Winsorize the outlier so that it has the same value as the next highest non-outlier value in the dataset. But if you have enough dataset, you can actually delete the entire case. So this is good. We have no outliers. And let's check for independence of observation, which we check by examining the independence of error using the Durbin-Watson test. All right, so here it is. Go into model summary and you'll find the Durbin-Watson test here. So the Durbin-Watson statistic is close to 2, and this is good because we don't want it less than 1 or greater than 3. So the assumption of independence of observation has all been met, and the only thing to check for is normality, which we can see in the PP plot here. All right. So the dots generally line up along a 45-degree line. So we have we have normality of residuals, and we can see that our dependent variable of online learning self-efficacy also nicely or somewhat somewhat normally distributed, like here. So the scatter plot of the standardized residual versus the predicted variable is elliptical, as it should be here. There is no pattern, or there's no discernible pattern. So all of our assumptions have been met. So now we can head on over to interpret our regression model. So going back to the top of the output window, we see descriptives. So this will be useful later when we write our model. We know that the means, the standard deviation, and that all 101 cases were used in the model. So the correlation matrix shows us that the variables correlate at 0.51. All right. This is, remember in our correlation lessons, this means that we have a moderately strong positive correlation. So the variables entered, removed box tells us that the only predictor in the model was flow and the only dependent variable was online learning self-efficacy. In the model summary, we get some other useful information. First, we get first we get the correlation, which is 0.51. Of course, you already know this because you have seen this in the correlation matrix table already. We also get the R, capital R squared, which is 0.62. 0.262. All right. So how do we evaluate the capital R squared? Remember that we used a lowercase r squared in bivariate correlation as what we call the coefficient or determinant or the term of determination. So if the proportion of variability in the outcome variable that was explained by the predictor variable, so here we have a capital R squared statistic. So the capital R squared statistic is still the coefficient of determination. But in regression, we typically use multiple predictor values to predict an outcome. So the capital R squared is the multivariate equivalent of the lowercase r squared for bivariate correlation. It still tells us the proportion of variance in online learning self-efficacy. Uh, syempre accounted for by flow. So the capital R squared for this equation is 0.262. This means that 26.2% of the variance in online learning self-efficacy was predicted from the level of flow. So again, capital R squared is multiple predictors. Lowercase r squared, you have one predictor. So here's something interesting. Although we are running a linear regression, but we have an ANOVA summary table here. Now, aren't those things different? Yes, but remember that regression, ANOVA, t-test, correlation are all part of the general linear model. So this ANOVA is just another way of looking at our regression model. And what this tells us is that our model with one predictor works better than simply predicting using the mean. So the significance value here means that our model using flow as predictor was significantly better than prediction without flow in the model. This means that there is a statistically significant relationship between our predictor and the outcome variable. So the notes underneath the table shows us the dependent variable and the predictor that is flow. Uh, yeah. So if this ANOVA was not significant, then the predictors you choose did not contribute to predicting the outcome any better than just using the mean. So now let's get on to the coefficients. This is an important box. So the ANOVA told us that our model works, but we want to figure out how it actually works. So there are two types of coefficients in the regression. You have standardized and unstandardized. For now, we're just going to stick with unstandardized coefficients. So now we need to find A and B as indicated earlier in our formula. So we can see B here, but no A, no column for A. Actually, both a and B are in this column labeled capital B. So remember that A is a constant. So this value of A is 51.602. That is actually our starting point. Then the B value is 0.812. Now the B coefficient has a t value associated with it. So this is a t-test to see if adding this variable as a predictor improves the predictive ability of the model. So now, of course, this would be more useful if we have more predictors, some of which were significant and others were not. So if a t-test for the beta coefficient is not statistically significant, then that tells you that this predictor does not add to your model. So ignore it. If, on the other hand, the t-test is significant as it is here, then look at the coefficient. So look at the sign. We have positive 0.812. So this tells you whether the dependent variable will increase or decrease due to an increase in the predictor variable. So here, here's how you interpret a coefficient. For every 1 unit increase in the predictor variable, the outcome variable will increase by the unstandardized beta coefficient value. This coefficient is positive, so we would read this as such. For every 1 unit increase in flow, online learning self-efficacy will increase by 0.812 points. So the standardized beta would be interpreted as for every 1 standard deviation increase in flow, online learning self-efficacy will increase by 0.51 of a standard deviation. And by the way, does the positive 51 look familiar? Can you remember where you have seen this before? Oh, yes. Uh, that was the correlation here between the two variables. And what is a correlation again? It is the standardized covariance of two variables. And beta is the standardized coefficient uh, of the relationship between two variables. So, uh, is it all starting to make sense right now for you? If it is, then that's cool because this is how you run and interpret simple linear regression using SPSS. Once again, my name is Dex Kamitan and thank you for watching.